Hello, everyone. My name is Karen Caicedo. I am a PhD student in the University of Bordeaux, and my project is funded by an INR. And today I will talk about my project, which is self-interference 3D localization microscopy in the near infrared for deep tissue single particle tracking. So let's get started. First of all, I'm gonna introduce the concept of superlocalization. So suppose that we want to image fluorescent nanobodies through a microscope. Even if we are working with the best microscope ever, the image that we are going to obtain is gonna look like this. It is like a blurry spot that we call the point spread function, PSF. Now, what happens if we want to image two fluorescent nanobits that are very close to one another? Well, in that case, the image that we're gonna obtain is gonna look like this. It's gonna look blurry, and we won't be able to resolve the localization of both emitters. And there is where superlocalization takes place. So if we have our sample of these point emitters of light spread enough so that we can isolate the image of the PSF of each of them, then we can super localize them and regenerate the image and therefore localize the fluorescent nanobits. And so super resolution microscopy, how does this work? What is the principle behind? So since we need to have some sparsity between each of the point sources, sometimes we cannot have that sparsity in time, in space. But the way that we resolve that problem is that having the sparsity in time by using the blinking characteristic of the fluorescent nanobits. So for each image that we make, different nanobits will be emitting light, and therefore we can super resolve the image. Otherwise, it will look diffraction limited like this, kind of blurry, and we won't be able to localize each of the emitters. Now, the typical localization precision that we can achieve is around 10 to 20 nanometers. This means around lambda over 30, where lambda is the wavelength of emission of these fluorescent nanobits. And this is the principle of one of these super resolution techniques, which is called the storm, and is the one that we use. So which are some popular 3D single molecule localization techniques out there? So in one hand, we have modification of the PSF shape techniques, such as cylindrical lens and double helix. And on the other hand, we have multiplane imaging. So for the first group, modification of the PSF shape, what we do is to introduce optical aberrations in a controlled manner. So for instance, here we have astigmatism. But the limitation of these techniques is that whenever we want to image or to use them to image inside a biological tissue, the sample may also introduce aberrations. Therefore, we cannot retrieve, and it will be problematic to retrieve the information regarding the localization of these emitters. And in the case of the multiplane imaging, the problem is that we have division of the photon budget. And whenever we image inside a tissue, we have a low number of photons from our signal. So if we divide it, we're gonna lose a resolution. Therefore, these two techniques have their limitations when applying to biological imaging. And this is the reason why we present a solution, which is self-interference 3D super resolution, SELFIE. So which is the physical principle behind SELFIE? So suppose that we want to image one of these fluorescent nanobits through the microscope. At the exit of the microscope, we can approximate the signal emitted by the fluorophore as a Gaussian beam. And this Gaussian beam has two terms, the intensity and the phase. And the phase is related to the radius of curvature of the light emitter. So now if my point emitter is not at focus in the microscope, then the light emitted will have a waveform curvature. And this waveform curvature changes in sign depending on the axial position of my emitter. Therefore, if we are able to measure the waveform curvature, we will be able to determine the axial position of my emitter. And how to measure the waveform curvature? Well, what we use is an interferometric method, which is self-interference. That means that the signal of the fluorophore will interfere with itself, creating an interference pattern. So regarding the optical setup of selfie. So originally, selfie was developed to localize dyes and quantum dots emitting in the visible spectrum. And this is how it looks, the optical setup. And I know that this setup looks a lot like the transmission light setup, but the diffraction grating that we are using is different. This diffraction grating is a phase-only 2D diffraction grating, which means that it has been designed so that we don't lose the number of photons that we have in our signal. So we have here the sample, right? Here we have the microscope, and we put the diffraction grating just before the imaging plane at the exit of the microscope. And then we collect this signal in our detector. So before the diffraction grating, if we don't put it, the PSF, the image of a nanobit, would look like this. But after putting the diffraction grating, the PSF will look like this with the interference pattern. You see? So a single image generated with selfie contains two independent variables, which is the intensity distribution, from where we can extract the intensity centroid and determine like that the lateral localization, the X and Y localization, and the waveform curvature, which leads us to the axial superlocalization. So if we look at this graph, what we see here is an example of images that we can obtain with selfie. So let's look at -400 nanometers. Here we have the interference pattern, but what happens when we compare it with +400 nanometers? See, the interference pattern is different. And that happens for each position along Z. And that is why from the interference pattern, we can retrieve the axial localization. And what is the localization precision that we can obtain with selfie? Well, it is below λ/30. So it is so we go, of course, beyond the diffraction limit. And in this case, for instance, of visible spectrum, the localization precision that we can obtain is below 20 nanometers. And this for a number of photons of around 1,000, which is the case when we have a real acquisition in biological tissue. So how do we retrieve the information from selfie? So what we do is to image a fluorescent nanobit that we are gonna use as calibration. And we make images for different positions along Z of this fluorophore. After, we calculate the Fourier space, the transform Fourier space, and we will have images of it for each position in Z. Now, to determine the X and Y position, what we do is take the intensity and make a 2D Gaussian fitting. And by calculating the centroid, we get X and Y. And now for C, what we do is to use the Fourier transforms, as a lookup table, so that we compare the Fourier transform that we have from an emitter in a real acquisition with the Fourier transforms of the calibration, so that we will know in which position of Z we are. Because if you observe, the Fourier transforms are different for each position. So how does an image with selfie looks like? So here's an image that we have obtained by combining the storm with selfie. And this is an image of F-acting filaments of human fibroblasts. And here we have the same image, but diffraction limited. So we can see that whenever we combine the storm and selfie, the difference is huge. So here the color represents the axial position of the filaments. And here what we can see is how the filaments distribute in depth. And the precision that we can obtain is around 20 nanometers for X, Y, and Z. Therefore, we can conclude that the resolution is more or less isotropic in the 3 dimensions. So another examples of applications with selfie is combining again the storm and selfie to image up to 56 microns inside spheroids of stem cells, achieving around 50 nanometers of precision, and also using selfie for single quantum dot tracking in brain slices up to 25 microns of depth. However, what happens if we want to go even deeper, like hundreds of microns inside the tissue? Well, in that case, we have to overcome some challenges when imaging biological tissue. First of all, we have the sample limitations, such as, for example, when we make slices of the tissue, we will have some tissue that is damaged in the edges. So we have to image deeper so that we can understand the biology behind it in a more accurate way. Also, if we want to image intact tissue, sometimes we have to go hundreds of microns inside the tissue to target whatever we want to image. Therefore, we need to find a way of how to go deeper inside the tissue. And we also have some optical limitations, such as aberrations, scattering, and absorption that will lead us to photon loss. Now, what is the way that we use to overcome these limitations? So there is a range of wavelengths of light, which corresponds to the near infrared regime, where the penetration depth in biological tissue is the deepest. And we can see, for instance, in this image, that it is very obvious that whenever we are closer to the red, the light almost trespasses the tissue. So when we are in the near infrared, the penetration of the light is the deepest. And it happens that carbon nanotubes are strong fluorescent emitters in this regime. And they are rolled up sheets of graphene, which are of the size of around 300 to 500 nanometers that have this particularity of emitting in the near infrared regime. So we widely use here carbon nanotubes in order to image inside biological tissue. And what do we do in our group? So we take mice, we inject the carbon nanotubes inside the brain of the mice. We take slices of the brain, and we use super resolution imaging techniques to image these nanotubes. And what we do is to follow the emission of the carbon nanotubes so that we can reconstruct the trajectories inside the extracellular space. And due to this interplay of the geometry of the carbon nanotubes with the extracellular local environment, we can understand and we can retrieve information of the extracellular space. But the thing is that all this has been done in 2D. However, the brain is a 3D object. Therefore, we aim to achieve 3D single particle tracking. So how to apply selfie on carbon nanotubes? So to do so, we have to redesign a new optical setup to make it suitable for carbon nanotubes. Why? Because in this wavelength range, things are different. We have different emission, wavelength emission, different diffraction rating, and we use a different camera, which has different pixel size, bigger pixel size. So the optical setup looks like this. Again, we have the sample, the microscope. After at the exit, we have the diffraction rating, and then we have the detector. And now in between the diffraction rating and the detector, we have magnification correction so that we have 3 pixels of the camera per fringe in the interference pattern. And we have chosen this ratio because it is the best in order to compensate signal to noise ratio and localization precision. So how do we calibrate our setup to know the precision that we can attain? So first of all, we have to make the sample preparation. And for that, we use immobilized diffraction limited carbon nanotubes. And we prepare our sample such that we avoid blinking and the signal is very stable. And then we excite these carbon nanotubes and we image them through our setup. And what we do is make a bunch of images along Z, and is what we see here in this video. So what we see, each of them are carbon nanotubes. And we see the interference pattern. And look, it changes depending on the position in Z. Therefore, we can retrieve the axial localization. Now, in order to analyze the precision of selfie in the near infrared, we have used the Kramer-Rao lower bound. And what is it, the Kramer-Rao? It basically tells us how fast the PSF changes as a function of X, Y, and Z. So it is an optical, it is a theoretical estimator of the precision of any imaging method that we are using. In this case, selfie in the near infrared. And the precision that we can obtain is always below 50 nanometers for the axial localization. That means that we obtain a precision of below lambda over 20, which is very high considering that we are in long wavelength regime. So as preliminary results, what we have been doing is diffusion of diffraction limited carbon nanotubes. So here we see a nanotube. It is slowly diffusing and we are able to track it. But of course, the thing is that we are not only able to track it in 2D, but in 3D using selfie. So as a conclusion, we can say that we have achieved axial localization precision below lambda over 20 for near infrared emission of carbon nanotubes, and we aim to apply selfie in single particle tracking of carbon nanotubes inside brain slices. Thank you for your attention.